Hello viewers, in my previous lecture on phospholipids, I had discussed with you phospholipids where there is ester linkage. That is, I had discussed with you the basic structure of phosphatidic acid. And you know all other phospholipids are derivatives of phosphatidic acid, which may be lecithins, cephalins, and so on. In this lecture, I shall be discussing with you ether linkage phospholipids. That is, in these lipids, phospholipids, we will have a ether group in them along with the ester group. So ether linkage, what are ether linkage phospholipids and where are they present? These phospholipids are present in some animal tissue and in many microorganisms. And what we find in these lipids, ether lipids, that they are different from ester lipids. How? In them the C1 or C2 of glycerol is ether linked with some long chain alcohol. And this long chain alcohol may be saturated or unsaturated. That is, it may be unsaturated in plasmalogen and it may be saturated in platelet activating factor. So what are now plasmalogens? What you have to remember, like phospholipids, like the one in which we have an ester group, in ether linkages, ether lipids, what we have is a glycerol backbone here. But how do they differ from the ester lipids, ester phospholipids? That in them there is a bond between a long chain alcohol, that is unsaturated alcohol, and the first OH of the glycerol. And this results in the formation of a ether linkage here. Then the second OH of glycerol makes a bond with the fatty acid, resulting in ester linkage. And the third OH again forms a bond, phosphoester bond with phosphate, which in turn forms another phosphoester bond with an alcohol molecule. And what you have to now remember is that how are these plasmalogens or ether lipids, phospholipids, different from the normal phospholipids? That is, in this case, we have a ether linkage at the first hydroxyl group of the glycerol, whereas in the other ones, we have a ester linkage here. And you have to remember, this part is the non-polar part and this part is your polar part. This is the head and this is the tail. Now let us go on to, if we look into the structure, so what do we find? That the C1 or the C2 of glycerol is ether linked with some long chain alcohol in this ether phosphoesters. And what we find here is, that is, when we talk of a structure of a plasmalogen here, what we find that it has a 16 carbon long chain with a double bond between C1 and C2. That is, it has a vinyl linkage, and this is linked with ether linkage, that is COC linkage at C1 of glycerol. And C2 of glycerol has an ester bond with a fatty acid. The phosphoryl group, which is present at the C3 of glycerol, may sterify with any of the nitrogenous bases, which may be serine, ethanolamine, or choline. So as now you can see on your screens, this is the glycerol backbone. And now here we have a 16 carbon unsaturated alcohol part. So what happens here is that the OH of the glycerol reacts with the OH of the unsaturated alcohol to form a ether linked here. And what we find is that this double bond is between the alpha carbon and the beta carbon, and rest of the chain is saturated. That is, we know that this will be CH2, 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 and this will be a CH3 group, and in all it has 16 carbons here. So this is a bond between two alcohols, that is a OH group of a glycerol and OH group of a fatty acid. Therefore, this is an ether bond. Whereas at the second carbon, now the OH, second OH of the glycerol reacts with a fatty acid to form a ester bond here. And the OH on the third carbon of glycerol reacts with phosphoric acid to form a phosphoester bond, and this phosphate then reacts with a choline molecule through phosphoester bond, resulting in formation of plasmalogen. Now this molecule, this nitrogenous base, may be choline, or it may be serine, or it may be ethanol amine in plasmalogens. So now let us look at where are these plasmalogens present. These plasmalogens are present in tissues of vertebrates, especially in the heart, in brain, as you can see here, and in the muscles. Now next what we have is, which is very, very important, is a platelet activating factor. Platelet activating factor is a plasmalogen which is involved in aggregation and degranulation, that is activation of platelets. It has protective effect against reactive oxygen species, that is, it can scavenge free radicals and prevents biomembranes or tissues from peroxidation. Now this molecule also has a 16 carbon saturated hydrocarbon chain linked to a C1 of glycerol by ether linkage, and the C2 of glycerol is esterified with acetic acid. The C3 has the phosphate group and choline. So now first let us see what is platelet activating factor. So if we look into the platelet activating factor, what you have to remember is that this is a ether phospholipid, and in this case the first OH of glycerol is attached to another fatty alcohol through ether linkage. The second OH is attached to a very small group, that is acetyl, that is, this reacts with acetic acid, resulting in an acetyl ester here. And the third OH is of glycerol is attached to a phosphate through phosphoester linkage, which in turn is attached to choline, and it results in platelet activating factor. Now if you notice here, first point that we notice here is that normally in all other lipids that we've discussed till now, this has been a fatty acid, that is, it has been a long chain carboxylic acid, whereas in here in platelet activating factor we have acetyl ester, that is, it is an ester of acetic acid and a hydroxyl group on the and an alcohol, that is hydroxyl group on the second carbon of glycerol. So that means it's a smaller ester. We know phospholipids are insoluble in water, but this one, because of the presence of the acetyl group here, it is, which is smaller in size, this is comparatively more soluble. The second thing which you have to notice here is what is the difference between a plasmalogen and platelet activating factor. In plasmalogen, this ether group, this alcohol, which is fatty alcohol which is present here, is unsaturated, whereas in platelet activating factor, this fatty alcohol is saturated. And rest, of course, this group will be again different here. So this is the difference between platelet activating factor and the plasmalogen. That is, here we have in platelet activating factors, the alcohol, the fatty alcohol present here is saturated, whereas in plasmalogen it is unsaturated. So what is the use of this platelet activating factor? Platelet activating factor, also known as PAF, is a phospholipid mediator. that causes platelet aggregation and dilation of blood vessels. And it also causes inflammation, allergic responses, and shock. When does this happen? Supposing toxins from fragments of destroyed bacteria induce the production of PAF, which leads to dilation of vessels and a drop in blood pressure. So supposing we've inhaled something, or we've taken toxins from the fragments of destroyed bacteria, we take it from the environment also. So what will happen is that those destroyed bacteria will induce the production of platelet activating factor, and when this platelet activating factor is activated, it leads to the dilation of blood vessels, and there is a drop in blood pressure. This may now result in reduced cardiac output and produces asthma-like symptoms. That is, you will have difficulty in breathing because there will be inflammation of the lungs. So now, till now, I have discussed with you two ether linkages, two phospholipids which had ether linkages in them. So what was particular about phospholipids? In phospholipids, if we see, we have a glycerol as a side chain, as the main moiety, and along with that it is then we have a ester linkage in it, which we call as ester phospholipids, or we have ether linkages in them, which we have sphingolipids in them. So in my previous lecture, in the previous part of this lecture, I had discussed with you the interesting information about glycerophospholipids. And what we found about this glycerophospholipids, that is the ether lipids or the ester lipids, that these lipids have a glycerol as a central alcohol molecule, which justifies their name glycerophospholipids. That is, in this case, in glycerophospholipids, as we've seen till now, glycerol is a backbone of glycerol-based lipids. That is, these glycerol-based lipids can be triacyl glycerols. That when I talk of triacyl glycerols, we are talking of oils, fats, or waxes, or they can be glycerophospholipids. And when we talk of glycerophospholipids, we are talking of glycerophospholipids where they can be a ester linkage like cephalins, lecithins, or there can be ether linkages just like in plasma activating factor. These are some of the examples of glycerophospholipids. And when we talk of a glycerol molecule, you know that in glycerol molecule is a trihydric alcohol which has 3 alcoholic groups on it. That is, it has an OH on the first carbon, second carbon, and a third carbon. So now I shall be discussing another class of lipids which is also important, which is sphingolipids. And in sphingolipids, the central molecule is sphingolipids, is sphingol or sphingosine. So when we are talking of phosphoglycerolipids, there the central molecule was glycerol. Whereas when we talk of sphingolipids, here the central molecule is sphingosine. And as you can see on your screens, a sphingosine is a 18 carbon molecule, and it has OH on the first carbon. This I can say is 1, 2, 3, 4, 5 and 12, 17, and this is your 18th carbon. And this has a OH on the first carbon, it has a amino group on the second carbon, and it has a OH group on the third carbon. So this is what you are seeing on your screens, that in sphingosine, the first carbon is attached to OH, second carbon is attached to NH2, and the third carbon is attached to OH. So what we mean here is the C1, C2 and C3 of sphingosine molecule therefore are comparable to 3 carbons of glycerol. So as you can now see on your screens, these are the 3 carbons of glycerol, and 1, 2, 3, these are the 3 carbons of sphingol or sphingosine. It means the same thing. Here the first carbon is attached to OH. In sphingol also the first carbon is attached to a OH. The second one is attached here to a amino group. Here the second carbon is attached to a OH. Then here the third carbon is again attached to an OH. Here also third carbon is attached to an OH. But what we note here is that to the third carbon, a long chain hydrocarbon is also attached to a sphingosine. So this is how we compare the structure of sphingol and glycerol. Please remember, glycerol forms the backbone of glycerophospholipids, whereas sphingol forms the backbone of sphingosine lipids. Now let me compare with you the structure of sphingophospholipid and glycerophospholipids. So first what you have to remember is that this is the schematic diagram for sphingolipids. So when we talk of a schematic diagram for sphingolipid, what you have to remember is that if a diagram is being represented by an inverted L, that means it is a sphingolipid. And what we find in sphingolipid, the first two hydroxyl groups, the hydroxyl group which is attached to a phosphate group and a amino alcohol, and the second one which is forming amide linkage, which is having an amino group, are important biologically. The third OH is not shown here because it does not take part in biochemical reactions. So, and now if we go and compare the structure with glycerophospholipids, what we'll find in glycerophospholipid is that this is the first carbon is attached to a fatty acid, second carbon is also attached to, second hydroxyl group is also attached to a fatty acid, whereas third is attached to non-nitrogenous base through a phosphoester linkage. So this is the difference between sphingolipids and glycerophospholipids. What you have to remember is in sphingospholipids or in sphingolipids, the backbone is sphingosine, which is a 18 carbon dihydric amino alcohol. Whereas when we are talking of glycerolipids, here the backbone is glycerol, which is a trihydric alcohol. So before I start with the structure of sphingolipids and what are sphingolipids, let us first concentrate on the structure of sphingosine, which forms the backbone of the sphingolipids. So what we find is, as I've already said, that sphingosine is a 18 carbon amino dihydric alcohol with an unsaturated hydrocarbon chain. So as you can now see on your screens, it is very important that you see on your screens here, that is the first carbon in sphingosine is attached to a OH, the second carbon is attached to a amino group, and the third carbon is attached to a OH here again, which is not important. This does not take part in biochemical reactions, and this carbon is also attached to a long hydrocarbon chain. In it, this sphingosine has 18 carbons in it, 1, 2, 3, 4, 5 and 12, 17, and this is the 18th carbon. And then we have a double bond between the alpha and the beta carbons. This is what you have to remember. This is the structure of sphingosine, and this structure will be the basic structure which we will find is present in all sphingolipids. And now you have to remember that sphingosine is biosynthesized in human body using amino acid serine, and this is this serine amino acid which provides the NH2 group of sphingosine. Sphingosine, as we had to discuss the structure of sphingosine in great detail, because sphingosine forms a primary part of all sphingolipids, and these sphingolipids are class of membrane lipids. So now if we talk of a sphingolipid, what do we find? That generally when we are talking of sphingolipids are a class of lipids that contain a backbone of a set of aliphatic alcohols. That is, it has a backbone of sphingolic bases, and these sphingolic bases may be a set of aliphatic amino alcohols, and these aliphatic amino alcohols basically in the structures which we are going to discuss, we find that this aliphatic amino acid is sphingosine. And now these lipids will contain a sphingosine, a fatty acid, and a polar group. So let us look what are sphingolipids. So we find that in sphingolipids they have a hydrophobic region, and this hydrophobic region is made up of long chain of sphingosine base such as sphingosine, which is linked to the acyl group of a fatty acid via a amide bond. So now if you look here, this is a sphingolipid, and as I have told you that sphingolipid is this basic structure. That is, in sphingolipid we have in a sphingosine, this group is NH2 group, and now if this one of the hydrogens of the NH2 group reacts with an acid to form a amide group here, what we will get is a sphingolipid. Now if this H here, if this group R here is H, then we will get the simplest sphingolipid, which is a ceramide, right? So a sphingolipid with an R group consisting of a hydrogen atom only is a ceramide, and the other R groups we can substitute there will be phosphocholine, which will then give us a sphingomyelin, and we can also have various sugar molecule monomers. If we have sugar monomers, or we have dimers, or we have oligosaccharides which is attached to the basic sphingolipid, we will get cerebrosides and globosides respectively. And these, as I've said, that ceramides are the simplest sphingolipids. What I mean by saying that ceramides are the simplest sphingolipids, what you have to remember is that when we replace hydrogen of the sphingosine with when we replace the R group of the sphingosine with H, it is a ceramide. This ceramide is widely distributed in small amounts in plants and animals' tissues, and all other sphingolipids are considered to be derivatives of ceramides. So now if we have to take a brief or remember what is a ceramide, you have to remember that ceramide is composed of sphingosine or a sphingol, which is we mean the same thing here, and a fatty acid. So this, as you can see on your screens, what we've done here is that we have a sphingol which is reacting with a fatty acid to form a ceramide. So what is happening in this case? Thus a ceramide is a fatty acid linked to an amino group of the sphingosine with an amide linkage. So what you have to see, what you can see on your screens is, like, if this was not R here, this was simply this R is H in this case, then this is a ceramide. So what do we say? What is ceramide composed of? Ceramide is composed of sphingosine, and you know what is sphingosine? Sphingosine is CH2OH, CHNH2, that instead of having a amide linkage here, we have a NH2 group here, and then we have this long chain unsaturated hydrocarbon here. So when this amino group reacts with a fatty acid, resulting in the formation of a amide, this will result in a ceramide. And what you have to remember here is that in ceramide, this R is H. That is, it is composed of, what do you say, a sphingosine or a sphingosine or a sphingol, which reacts with a fatty acid, resulting in formation of a ceramide. Now the group R, which is present in ceramide, is a hydroxyl group, and this hydroxyl group is hydrophilic in nature. So now what do we say? What are ceramides? Ceramides are a family of phospholipids molecules, and the word ceramide is derived from the Latin word cera, which means wax, and amide. Ceramide is a component of vernix gaseosa, the waxy or cheese-like white substance found coating the skin of newborn babies. This is very interesting. So as you can see on your screens, what we find that a newborn baby is covered with a white waxy sheet, which is known as vernix gaseosa, or which is also known as birthing custard. Do you know what is the importance of this sheet? This sheet protects the baby when in the fetal state, and even after some time its birth, this birthing custard will protect the baby, and this birthing custard is nothing but ceramides. Now ceramides, this is nothing but ceramide. Now where are these ceramides formed? These ceramides are found in high concentration within the cell membranes of eukaryotic cells. Ceramides are components of sphingomyelin, one of the major lipids in lipid bilayer, and ceramide can participate in a variety of cellular signaling like regulating differentiation, proliferation, and programmed cell death, which is also known as PCD of cells. For this lecture, I had again taken up the books by Bruce, Solomon, McMurray, and in my next lecture, I shall be discussing with you derived sphingolipids and cholesterol. Thank you.